Okay, number 31. This says if 15.3 moles of iron 3 chloride are produced when 12 moles of iron 3 oxide react with excess hydrochloric acid, what is the percent yield? Okay, so this is a stoichiometry problem and a percent yield problem. So there's two questions here in one. So what this question is really saying here is that like, let's say that we actually did this and we actually produced 15.3 moles of iron chloride. That may or may not be, probably not in this case, that's not going to be the amount of iron chloride that we should have produced. So remember that the percent yield calculation is just simply to take our actual production. This is going to be that number, by the way, over our theoretical or our accepted value, and then multiply that fraction by 100. So we're basically looking at, how much we actually made over how much we should have made. That's the stoichiometry work we're going to do, and then we're going to divide those two numbers and divide by or multiply by 100. Okay, so let's do the stoichiometry and figure out what that number should be. Okay, so this is a mole to mole kind of stoichiometry problem because we're not dealing in grams, and that's pretty handy here. So let's see. We don't care about that because it's in excess. We essentially know that 12 moles of iron oxide are reacting. So 12. This is chemical A, and we're really asking how much. Oh no, I'm sorry. 12 moles is here. This is chemical A. My bad. We're basically saying how much of this stuff do we make? How much of the iron chloride do we make? And then we're going to compare it to how much we actually made. Okay, sorry about that. Okay, so here we're going to use our moles of A, which is 12.0. 12.0 moles. And then here all we really have to do is look at the molar ratio. So the coefficient of our chemical A goes here. That's a 1 because there's a 1 coefficient. And of our chemical B, 2. That's the 2 that's there. Okay, so let's just see. I can probably do this one in my head. 12 times 2 divided by 1. That is 24 moles of iron chloride. Okay, so this, according to the numbers and according to the equation, we should have, in theory, made 24 moles, but we actually only made 15.3. And remember I said that typically your actual production in a chemical reaction is going to be less than what you think it should be. But now we're going to plug these two numbers into this, and so let's just do percent yield equals our actual production of 15.3 is what we actually made, boo, over what we should have made, which was 24. And then we're going to multiply this, which is going to be a decimal, multiply it by 100 to turn it into a percent. So this is 15.3 divided by 24. And multiply that by 100. Okay, so we only made about 63.75% of what we should have made. That is our percent yield, right? It's just basically a comparison between what you should have made, which in this case was 24, what you actually made, which was 15 and a little bit. So yeah, we made over half of what we should have made, but that's not a very good percent yield. All right. Moving on, number 32. Consider the following reaction here. Same reaction. This one says, if 20 grams of iron oxide react with 20 grams of hydrochloric acid, which is the limiting reactant? So we are not looking, we don't even care about the yield of our product here. We just want to know which of these two reactants is going to limit the production of our product. And so to do that, we are gonna basically just say, we're answering this question. If all of the iron oxide reacts, how much hydrochloric acid are we gonna need? And if we need more than we have, then we know that it is the limiting reactant. Or if we need less than we have, then it is the excess reactant, okay? So let's do the math here. We are gonna have to find the molar mass of these compounds, and those are, iron 3 oxide is 159.70, and hydrochloric acid is 36.46. Okay, so the math on this looks like so. Our setup is like this. I'm gonna use this as A and this as B. I'm just saying basically that I've got 20 grams of this, and how much of that is it gonna take to get rid of all 20 grams of the first reactant, okay? So I'm gonna say 20 grams of the iron oxide, which has a molar mass of 159.70. Got a coefficient of 1. Chemical B has a coefficient of 6 and a molar mass of 36.46. Okay, so let's look at the math here. We got 20 times 6 times 36.46 divided by 159.70. Okay, so the answer here is 27.40 grams of HCl. Remember, the question was, how much hydrochloric acid are we going to need to use if we want to get rid of all 20 grams of iron oxide? And it's going to take 27.4 grams of hydrochloric acid. And we actually have these in equal masses here. We only have 20 grams of hydrochloric acid. So we don't have enough to cover what we need. So that means that hydrochloric acid is the limiting reactant. Okay. All right. Number 33. Okay, number 33, kinetic molecular theory of gases. We talked a little bit about this in our gas laws unit. And so the question is this. Kinetic molecular theory of gas describes the various characteristics of gas and why that gas behaves in response to changes in temperature, pressure, volume, etc. Which of the following statements about gas and the kinetic molecular theory is correct? So going through these, you can probably you would probably land on the right answer anyway. But I'm just gonna share with you this. These are the tenets of the kinetic molecular theory of gases, and some of them are harder to explain than others. But it's basically just a description of the behavior of gases in response to things like temperature, pressure, volume changes, and things like that. And then just some general characteristics of gases. So I'm just going to blow through these so we've covered them. Gases are composed of large number of particles that behave like little hard spherical objects, and they have a state of constant random motion. The particles move in a straight line until they collide with another particle or the walls of a container. The particles themselves are much smaller than the distance between those particles, and so the volume of gas is mostly empty space. There is no force of attraction between gas particles or between the particles and the walls of the container. Now this is not totally true. This is kind of an ideal definition of a gas, but don't worry about that. Number 5, collisions between gas particles or collisions with the walls of the container are perfectly elastic. That just means that no energy is lost as particles collide with each other. And that's another one of those sort of ideal characteristics of gases. And then finally, number 6, the average kinetic energy of a collection of gas particles depends on the temperature of the gas and nothing else, which is not totally true either. But basically that just means that you know, the speed of the gas particles in their motion is depending on how hot the temperature is, and that's pretty accurate. So let's look at these options here. So the question is basically which one of these following is correct. So let's go through these. Gas molecules are tightly packed together without much room for motion. That is definitely not right. The gas molecules are far apart from each other. Gas molecules move faster when the temperature increases. Heck yeah, that's a pretty safe bet, right? And we learned that with Charles' law, where the temperature of a gas expands the gas because the gas is moving faster as it gets hotter, and the particles are moving farther from each other, and that spaces them out more and leads to a lower density. But anyway, so B is the correct answer here, but let's do these. C, gas molecules attract and repel each other. Not according to the kinetic molecular theory. That's just not right, even though there might be some truth to that, but for the most part, no. And gas molecules move very slowly. Yeah, I suppose if they were super cold, they'd be moving slow. But for the most part, gases, if they're in the gas phase, if matter is in a gas phase, the particles are moving fast. So really the answer, the only realistic answer is B. Okay. All right, number 34. Intermolecular forces are the attractions between neighboring molecules. Those intermolecular forces are weakest in which phase of matter? So again, our options here are going to be solids, liquids, or gas. So basically, I would just think, like, you know, the particles of a solid are tightly packed together. Their particles are fairly well attracted to each other, so they're tightly bound, even though they're not chemically bonded. Perhaps they're attracted to each other, which is why the particles are so close together. In a liquid, there's a little bit more mobility because the attraction between the particles is a little bit less. And then finally, in the gas phase, which we were just talking about, the particles are spread far apart. And that's because the particles are just not very attracted to each other. So the phase of matter in which those intermolecular forces are the weakest is certainly the gas phase. Okay? All right, number 35. Which of the following molecules would you expect to be the most soluble in water? Due to having a high concentration of electrons at one end of the molecule and a lack of electrons at the other. Okay, so this is all about polarity. And remember that in class we talked about this as like dissolves like. And so basically what we want to know, we got to know something about water, and then we got to examine these molecules too. So water, if you remember, is a molecule that looks like this. It is highly polar because we've got this really concentrated negative portion of the molecule up here due to the electronegativity of oxygen and these lone unbonded electrons that sit on top of oxygen. And that leaves the hydrogens both being very partially positive. And so we've got, you know, these a negative portion of this molecule and a positive portion of this molecule. This is where we say this is polar. Okay? So like dissolves like just means that polar substances will dissolve in other polar substances. So what we're looking for here is one of these molecules that is also polar, so that it will dissolve into water, okay? And so there should be some electrons on these guys. There we go. Okay, so let's take a look at here. This first one, this is fully nonpolar because it's symmetric, right? We've got loads of electrons on both ends of this molecule. So this one is what we would call nonpolar, meaning that it doesn't have two diametrically opposed poles. You know, each end of the molecule, each pole of the molecule is the same. So this one's not really polar. let's jump. So this one's out. That is not the one that's going to dissolve in water. This one, let's take a look at it. This one, you know, even though it's not a fully symmetric molecule, the area of high concentrated electrons is kind of in the middle here, which means that it's not. This is mostly nonpolar as well, and so this is going to ultimately end up being our answer. But let's talk about why. It's because these hydrogens are somewhat positive over here, and then this end of the molecule over here, this is a very partially negative portion of the molecule. And so, you know, this one we would say is not very symmetric. It's certainly the least symmetric of our options. And so when we're looking for a polar molecule, we're looking for asymmetry of the shape, essentially, and that's this one, and that is going to be the one that is most soluble in water. Okay.